the character? Name one character from it. That's very good, Josh. Because I feel like the teacher from Billy Madison, who is...
It's in the pen, and I saw these things in the pen.
Oh, is it? It's a fun movie. I'm just sad that I'm old. Okay. All right, one-sided limits. Again, we're going to look more at why the limit from the left could be different than when it's coming from the right. And the primary example is definitely piecewise functions. Although you're not always going to have the visual in front of you. When the visual is in front of you, it's obviously quite simple. When you're approaching 1, which is here, from the right, your limit is what? I heard 1 and I heard 4. You're approaching 1. From the right, when you're asked for the limit, you're looking for the y value that it's approaching. As the x value approaches 1, the y value is approaching 4. And if we're approaching 1 from the left, the y value is approaching 2. And then we say, what would the overall limit be? What'd you say? No. There was a takeaway from yesterday that you missed, Taylor. Does anybody know? It's not 4. Correct. It does not exist. The limit, in order for the limit to exist at a number, it has to be the same from both the left and from the right. Okie doke. So the intention of the graph as it's approaching 1 from the right is pretty clear. The intention of the graph as it's approaching 1 from the left is clear. But overall, as it's approaching 1, it's giving you mixed signals. So you cannot say what its true intention is. Now, if I didn't have that, okay, let's think about this. If we're approaching 1 from the right, we would be plugging in values that are greater than 1, correct? So then which formula would you plug that into? Right, where x is greater than or equal to 1. So we would, if you plug 1 into there, do you see 1 plus 3 is 4? Okay? Knowing that this piece of the piecewise function has an endpoint, a solid endpoint, because of the or equal to, at 1, comma 4, that gives you that limit coming from the right. Your limit coming from the left, you would plug in numbers less than 1. That would mean to this equation. We can still plug 1 into this equation. It's going to be an open circle, obviously, on our graph. So this particular piece ends at 1, comma, when you plug 1 in, you get 2. So there's a point at 1, 2, and there's also a point at 1, 4. It's just this one's open and this one's closed. That open circle, that open point, is your limit when you come from the left-hand side, because you're coming from values under 1. Does this make sense? And then again, still you'll see they don't agree, so the limit does not exist. So let's look at this in symbolic form. The limit of a function as x approaches a number a is going to equal L, which is some value, if and only if. So that's only going to happen if the limit as you approach a from the right equals L and the limit as you approach a from the left in the function equals L. So just the symbolic definition of the limit from the left has to equal the limit from the right. If they both equal the same L value, then the overall limit is L. Are you guys familiar with the phrase if and only if? Have you ever heard that before? Let me go back. Do you know how to read this in math? Have you ever done if-then format? Okay, this symbol means if then. So if P, then Q is how any math person would read that. If P happens, then Q happens. And then you would read this, if Q, then P. Okay, so let's think of an example. If it's raining, then I carry an umbrella. So P is going to be if, I'll say P is going to be it is raining. It is raining. Q is I am using an umbrella. So this says, if it is raining, then I am using an umbrella. This one says, if I'm using an umbrella, then it's raining. If both of those are true statements, that you tell yourself if it's raining, you're going to use an umbrella, and the flip-flop is true, that you're telling yourself, if I'm using an umbrella, then it would have to be raining. In other words, I'm not going to use an umbrella for any other purpose. Yes? Okay? Then, rather than put those as two separate statements, this is a math symbol that means if and only if, which means that if-then logic can go both ways. So that means if and only if means the logic goes both directions. Because sometimes if-then statements only go one direction, meaning if I have a golden retriever, then I have a dog, right? That's 100% true. If you own a golden retriever, then you own a dog. The flip of that is not necessarily true. If you own a dog, then does it have to be a golden retriever? No. So that wouldn't be, and it's called a biconditional. This one doesn't have to be, but we're saying that it will be. What has to be a biconditional? What statement? How about a polygon having three sides and a triangle? If it's a polygon with three sides, then it's a triangle, correct? The flip of that is also true. If it's a triangle, then it's a polygon with three sides. So that is like a definition is usually biconditional, can go either way. Does this make sense? Okay? Something like, if it has four sides, well, let me go backwards. If it's a trapezoid, then it has four sides. That's true. But the flip of that is not true. Because if it has four sides, does it have to be a trapezoid? No. Okay, so there's kind of cases like that. So when we see if and only if, that means both things are true. So if you know that the limit coming from either side is both L, then you can conclude this. Or vice versa, if you know the overall limit already, then you can conclude that coming from the right and coming from the left, it would be the same thing. So the last thing I'll write is that in math, we abbreviate if and only if often using IFF. So that's a little side math notation lingo thing to throw at you, because you've obviously never done. You didn't do truth tables at all in geometry? Or like if-then statements? Okay. You did?
I do that like all
You
the
think you
time.
did, Maria? You use that arrow a lot. Okay, never minding.
I use it a lot in coding.
Okay. Here is a piecewise function, but also has some hole in it there, and then these two pieces are both open-ended, and the actual function value is elsewhere. So kind of an interesting graph, but again, when we're looking at a picture, I think it's a little bit easier. This says, what is the limit of the function if we approach -2, which is here, from the left? So what is the value if I'm approaching that from the left? What's the value? What?
0.
0. Why, Stephen, what made you say negative 1? But you're just looking at approaching from the left, so don't let these other points throw you. If you're approaching negative 1 from the left, the graph's intention, even though it's never going to reach it, the graph is infinitely getting closer to 0. That's the value of f of negative 2. So you gave me this. That's negative 1. And then the limit, if we're approaching negative 2 from the right, ignore these others. If I'm approaching negative 2 from the right, what is the graph's y value getting infinitely close to? Negative 3. So even though it's not reaching it, it's getting infinitely close to it. And so what is your overall limit as you approach negative 2? Does not exist. You ever seen Clueless? Once you set the limit, does not exist. Do you know that part? Ellie does. Oh, Mean Girls. Oh. I'm going to just give up with movies, okay? Just giving up. Limit of the function as we approach 0 from the left. Take a minute to think about what you want to write down for that. Haley, what do you think? What's its intention as it's approaching 0 from the left? What is the y value getting infinitely closer to, even though it doesn't touch it? 2. Think about when we approach from the right. Lily? 2. The overall limit, Adam? 2. And f of 0, Nathan Z? 3. So these two agree, which makes your overall limit exist. What did we learn yesterday? The fact that these two don't agree tells us what? The graph is blank. Discontinuous. Discontinuous at 0. It's continuous in other places and along other intervals, but specifically at 0, there's a point of discontinuity. There's a moment of discontinuity. Okie doke? All right. Graph each function, then use your graph to find the indicated limit. So 1 over x squared. Let's review rational functions. Where's the vertical asymptote? 0. Because that's the 0 of the denominator. Not only that, but it's a vertical asymptote with a degree of 2. What does that tell us about what's happening on either side of that? Right, they both go whatever direction they're going in, whether it's positive infinity or negative infinity, they're going together. And then what about our horizontal asymptote? Where's that? Do we have one? Small over big, as far as the degree is concerned, means it's at 0, correct? So if let's go to the right of 0, like at 1. If you plug in a 1, is that going to give you a positive output or a negative? Positive. So it's going to put you in this first quadrant, which really tells you everything you need to know for this sketch. It's approaching positive infinity, and the end behavior is being guided by that horizontal asymptote, right? Think about plugging in a number. You can't plug in positive infinity, but think about plugging in 1,000,000. 1 over 1,000,000 squared is going to be pretty darn close to 0. Hence the horizontal asymptote guiding that end behavior. And on the left-hand side, same thing. No matter what you plug in, a -1, that squared is going to make it positive, so it'll be a positive. So there you have that similar behavior on either side. And then, again, you can't plug in negative infinity, but you can plug in negative 1,000,000 and just think about it. Negative 1,000,000 squared is going to be a giant, giant, giant positive number. And 1 over a giant positive number is going to be pretty darn close to 0. So now, what is the limit as x is approaching negative 1, which is here? Since the graph is continuous there, whatever the function value is going to be your limit answer as well. So you just really just have to plug in negative 1. 1 over negative 1 squared is 1 over 1 is 1. We're going to talk about it now just because it is right in front of us. The limit as x approaches 0. What's the graph doing as it approaches 0 from the right? Positive infinity. What is the graph doing as it approaches 0 from the left? Okay, so they're both positive infinity, right? So is there a limit? Right, so we can kind of think about limit for what it actually, that word means. There is no limit, so technically that does not exist. But what you will find is that there are more specific ways to convey that some limits don't exist. Like for this one, you may see, and we will often do it, that this limit is positive infinity. You don't really need your positive sign, but I put it there. Saying that a limit is positive infinity is still saying it doesn't exist. Okay, it's just a more specific way of communicating what that graph's behavior is as it's approaching 0. So it's a version of does not exist. It's just a more specified version of does not exist. Okay, so that may come up. In exercise 2 here, before we jump into graphing, we can factor and reduce, yes? So we have x plus 2, x minus 2 up top. That cancels. So this simplifies to being very similar. I'm going to put an asterisk next to that because that's not truly the function. But those two different functions are essentially going to look virtually identical, and they're going to look pretty much like this line x plus 2. So y-intercept at 2 with a slope of 1, with the exception of what? A hole at 2, which we can see the location is right here at 2, 4. You can see that that's the location of the hole, or you can plug into your simplified version, you would get 2, 4. So what is this graph's limit as x approaches 2? Well, here's 2 from the left and from the right. Those arrows are kind of pointing at each other like that. That limit does exist, and the value is 4. Okay, we will sketch these, but I actually want to talk about how to approach this if you don't have the sketch in front of you. They want the limit as you're approaching 0. Okay? So we're going to look at behavior if we're approaching 0 from the left. That would be this equation. When you plug 0 into there, what do you get? So as you're approaching 0 from the left, you have a limit of 4. It's going to be an open circle. So that's not the function value there, but that's the limit as you're approaching 0 from the left. The limit as you're approaching 0 from the right uses this equation. So what do you get for that limit? 5. So they do not agree, and therefore the overall limit as you approach 0 does not exist. If the limit doesn't exist, then there's no way that we have continuous going on anyway. But just for the sake of asking it, what is the value of f of 0? Right. F of 0 equals 5, so it agrees with the limit coming from the right, but obviously doesn't agree with the other limit. So if the overall limit doesn't exist, then there's no way it can be continuous. But if all three of these agree, then it would be continuous. So this graph is x plus 4, y-intercept of 4, open circle, and a slope of 1, but this part of the graph is only existing when x is less than 0. And then outside of that, it's just 5, which is a flat line, anywhere x is greater than or equal to 0. So when you look at that, it's pretty clear that the limit coming from the left and the limit coming from the right are different. And you clearly have a discontinuity as well. Okie doke. Before we graph this, let's think about the limit coming from the left. So the limit coming from the left would mean use this equation. We're looking for it at 0. So even though it's going to be an open circle, what's your limit as you approach 0 from the left? 0, right? You essentially plug 0 in here. Limit as you approach 0 from the right uses this piece, and you plug in 0 there. Cosine of 0 is 1. So the overall limit does not exist. And then we'll sketch this in a minute, Steven. Well, piecewise functions in general. If this just said, this is what I was getting at. If you just said, what's the limit as x approaches 0, and you just plugged in 0 and said, okay, 0 is a part of this piece, so I'm going to plug it in there, and then I'll say the answer is 1, you'd be wrong. Coming from the left and from the right, you can do that on a piecewise function always. So this graph is x is less than 0. We just have a line with a slope of 1. Line y equals x. And the cosine of x starts at 0, which is, I'll just make this, well, I have to make this 1 because I already did rise 1, run 1. Oh boy, our cosine curve, but I already scaled it by 1. When does our cosine curve have to end? What'd you say? 6.28, right? 2 pi. But I already didn't scale my x-axis in terms of pi. I scaled it by ones to do my line. So I'm going to do 1, 2, 3, 4, 5, 6.28 is approximately there. 3.14 is approximately there. And then I'm just going to eyeball it. But you get the point. The focal point is here. What's happening as we approach 0? Limit does not exist. And without the limit existing, continuity is completely off the table. Okie doke? Well, these just aren't long enough, are they? So, let me just think about something real fast. Page 1014 is your homework. The limit can exist without continuity. Great if then by conditional thought process. So you just said if the limit exists, then it's continuous. True or false? Is that a true or false statement? True and false means, if you say true, that means always true. If the limit exists, right, then it's continuous. True or false? Because here's an example of where the limit exists. The limit exists, but it's not continuous. You see? So if you can find one example of something that, it's called a counterexample, right? If you can find one example that refutes this claim, like I just did, then you have to answer false. Okay? Which true and false by nature means if you're answering true, that means always true. Okay? Any questions on that? So if I say a dog is a golden retriever, true or false? False. Your immediate response is, well, sometimes it is, right? Like human to human, that's our immediate response. That means false. Because you can find a counterexample, you can find lots of them, where you have a dog that's not a golden retriever. Follow? Now, the flip of that, if it's a golden retriever, then it's a dog. True or false? True. Okay? So the flip of this one, if f of x is continuous, then the limit exists. Okay, so what's your counterexample? Find me something that's continuous without a limit existing. Right, this is true. If something is continuous, meaning there's no break in action, then that's solid because there's no break in action, then the limit has to exist. So that one would be true. So Stephen, whatever you just said, what did you say? No, you said it the other way around though. Yeah. You said if the limit exists, then it's continuous, and that's a no. But the other way around is a yes. Okay? All right. Hold on. 10:14. 27 to 31, you're just going to have to answer a bunch of questions, so I don't think we need any help there. 33 to 53. Asks us to graph each function, then use your graph to find the indicated limit or state that the limit does not exist. So let's look at the even ones. Any there that you think might pose an issue? Well, sketching graphs. A line. What's this? Parabola. What's this? Absolute value. So is a line continuous? Yes, always. Is a parabola continuous? Yes. Is an absolute value continuous? Is a rational continuous? No. There are moments of discontinuities on rational expressions because we have vertical asymptotes, right? Those are moments of discontinuity. So at those asymptotes is where you'd be nervous that the limit might not exist. It'll exist everywhere else, right? But at vertical asymptotes, it may not exist. This one, again, this one's not going to have a vertical asymptote. That's one I actually stole for your notes. It's not going to have a vertical asymptote, but it is going to have a hole at 2. So your limit's not going to exist there. How about the natural log graph? There is an asymptote at 0. So this one's actually worth looking at quickly. First of all, you need to know what your log and exponential parent graphs look like. Here's an exponential parent graph, right? Some base to the x power. Here's a log parent graph. y equals log with some base b of x. Yes? So this is a continuous function everywhere, but this, unlike the other examples, the line, the parabola, the absolute value, this has a limited domain in the sense that it doesn't ever cross here. So if someone asked you what's the limit as this graph approaches -5, you'd have to answer does not exist because the graph doesn't even get over to -5, right? Is it continuous at -5? No. It's almost like a weird question to even ask, but you'd have to say it doesn't exist, or it's not continuous at -5. A graph can't be continuous in a location where it doesn't even exist, right? Your limit anywhere in here is going to be fine. You're not going to have a problem because we're continuous the whole time, so you'll have a limit. But Jalen is correct in that as you approach 0, though, your limit will not exist. If you wanted to be more specific about that, you could say that the limit as you approach 0 is -infinity, right? But that's just a more specific version of does not exist. So in other words, if it was a multiple choice, you would never have the option of does not exist and -infinity because they would both technically be acceptable. Does that make sense? Okay. And then your cosine trig curves. We obviously saw an example of that already. Oh, then you got your bunch of piecewise. So your piecewise functions. Yes, you need to be able to sketch those, but eventually we should be able to do those without a sketch. Like for 52, for example. Test it coming from the left, plug in 1. Test it coming from the right, plug in 1, and see if they're the same. If they're the same, awesome. If they're not, will they be the same here? What's the limit as you approach x from the left, or approach 1 from the left? 3. What's the limit as you approach 1 from the right? 3. So that one, the limit would exist. What that means, hold on, for a piecewise, is that wherever this first graph ends with an open circle, technically, also is the location where this other one begins and then closes up that circle. Do you follow? So you get lucky in that sense because the break in action from piece to piece kind of has those two pieces molded together, which is not always the case, obviously, with piecewise functions. Let's look at this. '55 and 56. Adam, do the honors and read that for me, please. 55, the instructions. about those shortcuts.